Well, welcome everyone. Thank you all for coming this evening. I'm John Toole. I'm the Executive Director and CEO of the Computer History Museum. You may have noticed a little change in what we call ourselves these days. We've shortened it up. We've created a new logo, a very exciting logo, we believe, and you can see it right in front of the podium. So the Computer History Museum is what our new image and logo is going to be. It's not only, it represents the artifacts of the information age, and of course our mission is to really preserve the stories and information of the information age. And I think you're going to see more and more of that over time. It's what we call a soft rollout because we've been so operational for so many years, and we're really, really excited about it. Tonight's sort of a special evening. Stump the Professor evening, I think it's called. Questions answered, questions posed. But before I introduce Don, I wanted to show you a little different type of introduction. Most of you have seen my PowerPoint presentation. Don warned me that I should never, ever expect Don to use PowerPoint. So following that tradition tonight, Don, I thought I would share with you a very short video clip that was done by Channel 36 News in last August, which actually captured the spirit, I think, very nicely. Sharon Chin did this back in August, and you'll see Len Shustik and myself and a few others in it. So could we roll the video, please?
BMPC, but there are many other computers that came before and after it. And a lot of them are in warehouses at Moffett Field, waiting to be displayed in a new museum. Sharon Chin gives us a peek at the proposed Computer Museum History Center.
This looks like a big red calculator, but it's a 1965 kitchen computer that stored recipes. It was featured on the front of a Neiman Marcus catalog.
For $10,000, you could get the computer, complete with a chopping board, and an apron, and a cookbook, and a 2-week programming course, which is what it took to make it work.
It didn't sell well, but it's part of computer history. It's among thousands of pieces stored at this Moffett Field warehouse. The untrained eye may see tangled wires and old equipment, but to computer junkies and history buffs like John Toole, this is treasure.
Nowhere in the world can you experience up close and personal the collection that we've got. This is probably the world's largest collection of computing artifacts.
Toole and others are trying to raise $100 million to build a Computer Museum History Center at Moffett Field. It would sit on 3 acres of land in the proposed NASA Research Park. Most of the artifacts date from this 1890 census counter on. Museum Board Chair Len Shustik showed us around. This supercomputer's power heated up the bench.
This was one that came out in 1965, and people call it the world's most expensive love seat.
This computer tracked incoming missiles from the Russians in the 1960s.
This machine was amazingly enough reliable. Even though these vacuum tubes had a mean time to failure of about 3,000 hours, that means every 10 minutes you'd expect one to go out.
You might even recognize some of the pieces.
It was the first computer by Apple Computer. It was the Apple I.
200 tons of artifacts are stored here, half of them from a Boston museum that closed. Many are one of a kind, like this 1954 Johnniac. It was one of the first computers to have both program and data stored in memory, and it was almost lost forever.
It was sitting out in the back parking lot getting rained on when a couple of the people who had worked on it originally discovered it, called up the Boston Museum and said, please rescue this machine, it's an important artifact.
In fact, there's a bit or byte of history behind every item, and museum organizers want to preserve their stories.
Enshrine kind of the pioneers and the technology stories that are going to be important. And I love it. It's a great job.
Organizers hope the Computer Museum will break ground in 2003 and open in front of this historic hangar in 2005. There are public tours available from the storage site on Wednesday and Friday afternoons and by appointment, but you do have to call first. In Moffett Field, Sharon Chin, Silicon Valley Business.
From old to new, the world's most powerful computer.
Thank you very much. So I think Sharon did a great job to capture in a very quick way kind of what we're all about. And I welcome you all to join us in every way you possibly can. We're beginning, this is a wonderful lecture that's sort of toward the end of our lecture series, but we have a couple of great ones coming up. Eric Schmidt is going to be here December 6th. Unwinnable Wars, Personal Perspectives on Technology Leadership. And November 20th at Stanford, at the Gates Building, David Stork, who is with us here this evening, 2001 Hal's Legacy. There's a 90-minute new video on Hal's Legacy that will be aired shortly, and he's going to have a lecture on November 20th. I think we'll have a lot of fun with that. And I might also close in saying that our annual campaign will be beginning very shortly, so please help support us. It does take some money to make all this happen and to put these kind of public lecture series on the map. And we're very proud this evening, and I want to switch gears a little bit to talk a little bit about Don Knuth, because Don, not only have you seen him at many of our lectures, is really one of the major pioneers of the time. He's done so much, and it's called his Art of Computer Programming, volumes 1 to 3, and of course he's working on volume 4. And of course, there'll be a lot of questions along those lines of what he's really been involved with, but virtually everything in programming. His students, everyone, he's had about 28 PhD dissertation students, I think, that have got their PhD under Don. He's been a member of the American Academy of Arts and Sciences, the National Academy of Sciences, the National Academy of Engineering. He's a foreign associate of the French, Norwegian, and Bavarian Science Academies. They abbreviated that, so I didn't have to pronounce all that in different languages, Don, but feel free to do so when you get up here. He received the Turing Award from the Association of Computing Machinery in '74, the National Medal of Science from President Carter in '79, the Steele Prize from the American Mathematical Society in 1986, and a whole number of medals from foreign locations, from Sweden and so on, the Harvey Prize from the Technion of Israel in 1995, the John von Neumann Medal from the Institute of Electronic Engineers in '95, the Kyoto Prize from the Foundation in 1996. So I can't think of many other honors. The only one that I haven't referenced, of course, is the one that perhaps I'm the most proud of because he's a museum fellow. Please welcome Don Knuth this evening. Thank you.
Okay, thanks a lot. I've never seen such an illustrious audience in all my life. This is great. I see some people standing in the back, but there's also a couple empty chairs in the front. So, yeah, please come down. I'll be more comfortable. Now let's see if this is going to work. I'm going to see if I can get to my home page. Let's try this. Is that going to work? Let's see what happens. Maybe a slash. Okay. Now. I just put my home pages up here in order to, as a crib, to help people think of questions that if they don't, my main goal tonight is to answer every question that you put to me. And it's because, well, a lot of you took classes from me at Stanford, and you know that it was a tradition, the last day of class was always all question answer day. And now that I'm retired and not teaching anymore, I still like to do this. And it was always fun when I was at Stanford to find out what the students really wanted to know. They didn't have to come to the last day if they wanted to. They weren't allowed to ask any of the questions that were on the final exam. But otherwise, I tried to answer everything that was their last chance to get what they paid tuition for. Now, another way of saying it is that I really haven't prepared tonight. I'm just winging it. And the reason is that I'm writing volume 4 of the Art of Computer Programming. So I haven't got time to prepare any lectures, obviously. So, but you might also say that, well, I spent 63 years preparing for tonight, just, learning how to answer questions. So that's what, that's the basic idea. Now, on my home page, I have a place for frequently asked questions. I don't want you to ask those tonight. Yeah. I mean, you can always look those up on the web, right? The computer musings, these are talks that I give at Stanford that are open to the public, and there's going to be one on December 6th, unfortunately conflicting with the next Computer History Museum thing, but I'm going to be talking about squishing spiders on December 6th. If you always wanted to know about that, my news page has a bunch of stuff on it. A new grandson. My mother-in-law unfortunately died. I have various. Here as I'm working on volume 4, I'm using a lot of examples based on puzzles and classical recreation, and so I prepared indexes to literature, and decided I might as well put them on the web so that other people can use it too. Let's see, what is this here? This, well, I don't know how to use this version of Netscape, sorry. Okay, so what do we got here? Yeah, this one, I can't resist showing you this one. Beam me up, Scotty. This was the greatest surprise. I found out that that there's a minor planet named after me this year. So I was like, so now anyway, sorry about that. Okay, so and here it advertises tonight's lecture. So here we are, Computer Museum History Center. I'm just checking to see if it works. Okay, so I'm ready for questions. That link doesn't seem to be working, right? So forget it. Oh, here we go. Slow. Okay, there it is. Computer Museum History Center, which is now called the Computer History Museum. All right, so who's got the first question? Go ahead, say it. I'll repeat.
This is a question having to do with history and research priorities in publishing. In
Okay.
September of 1966, Richard Atkinson and Duncan Hansen published a paper in the Reading Research Quarterly called Computer-Assisted Instruction in Initial Reading, the Stanford Project. And a short paragraph from there is, in September 1966, the CAI reading program will be used with approximately 100 first-grade children in Brentwood School, which is located in a racially mixed low-income area of East Palo Alto. Currently, a building is being constructed on the school grounds to house the computer system and student terminals. Now, that was 40 years ago. Today, it's 2001, and people are talking to their computers. All over the world, people are using speech recognition for dictating letters and memos. But there's only about 5 projects that I'm aware of that are using speech recognition systems to help assess the oral reading of children. At Carnegie Mellon, Project Listen at the Oregon Graduate Institute. IBM has 2 at Vanderbilt and University of Texas in Austin. And there's another small company here in the Bay Area that doesn't have a product yet. In fact, there is no commercially available system that will use speech recognition to assess the oral reading of children. Now, I've written such a system as a hobbyist in my spare time, and I've included a feature for, yes, yes. As I said, my question is, would you please recommend a publisher?
Oh, okay. Well, I said we have an illustrious audience. Certainly, that's not a frequently asked question. I would say that you don't need an agent to get a publisher, but I don't have personal experience in any of those things. I know Dick Atkinson slightly, but in these but questions like that are actually foreign to my experience. So you have also succeeded in stumping me the very first time. Now I have a question over here.
Hi there.
Yeah.
Imagine that you are creating a new computer, a new machine, and this machine is a processor, an execution engine for instruction sets. And
I can imagine that very easily.
yeah, imagine that. And the only thing we know about this machine is that the design of the machine is such that it's designed to efficiently execute an arbitrary set of high-level languages.
An arbitrary set of high-level languages?
Yeah. That's very broad. That's not really central to the question.
Okay.
So I'm going to ask the question, and then I'm going to frame the question a little bit.
All right.
The question is simply stated. What is the best choice of word size, native word size for the machine? And if I want to frame the question, I want to just frame the question first by stating what may be obvious in that already I need 64 bits to address disks. And I may likely need more in the future. Is 64 enough? And obviously, as the word size increases.
Okay, so yeah, my answer is 64. You got it. It's a wonderful number. That's going to be my age next year. My millionth birthday is coming up in January. I'm going to be 1000000000. the computer I designed, MMix, as a 64-bit word because John Hennessy told me to make it that, and I found while I was doing that there were many good reasons for 64. Also, I learned how big 2 to the 64th is, which makes me very sure that you're not going to run out of address space. If you I mean, you can always do it stupidly, but no, this is. But the fact is that there were lots of uses. For example, the fact that 64 is equal to 8 by 8. So I could make instructions that worked on 8 by 8 Boolean matrices, and it was just a lot of revelations like that came by that things became clean when you started looking at 64. So, and after that, 69 might be the next best. Okay, that's a joke. We used to have a joke in college. The definition of a college man was somebody who couldn't count up to 70 without laughing. Yeah.
Don, can you move your mic up?
Can I move my mic up? That's another. You stumped me again. Okay.
But
yeah.
I cannot recall ever knowing why.
Yeah. Okay. So there was an article. So I'm not sure if it was Australia. There were Soviet and several Polish computers that used was it -3 or negative?
The one I read about was
-3. Okay. Well, that's no. It wasn't -3. It was balanced ternary, which means that the digits were -1, 0, and +1. And it's because in Poland they didn't have flip-flops; they had flip-flap-flops. But actually, balanced ternary is quite beautiful because in this system, if you want to round, you just truncate. It's exactly the same. And if you want to take the negative of the number, you just flip the sign of all the digits, and so on. There's many pleasant properties to balanced ternary arithmetic. And if it just has this little problem that it's easier to build binary than ternary. But if we had if it would turn out that chips would handle ternary just as well, then I think we'd all be using it. Now, but there was an article about the history of this, and it was in the Annals of the IEEE Annals of the History of Computing sometime in the last 2 years by a Polish author, obviously.
So out of all of the hacks that you've studied over all of these years, what's the best one?
The best hack? Okay, so now I was hoping nobody would ask some of these top 10 type questions where somebody says rate the best ever, because I can never answer those darn things. So what kind of a hack are you talking about? A display hack or a video or a programming? A what? Programming technique, a programming trick. Well, Bill Gosper's here tonight. The one that I'm thinking, he's the one of the authors of the famous hack mem, which was this memorandum from MIT. One that I love is that I haven't had a chance to put it. It's going to be in volume 4, but it's I think 4 instructions that you do in binary, and it converts the number to the next number, the next largest number that has the same number of 1 bits in it. You remember that, Bill? Yeah. So that's probably the best. Okay. Thanks. Yeah. Okay, now I got to go over to this part of the. Why did somebody ask me about one of the books I've written or something? Basically that's what I do is write books, and one thing I wanted to show you on my home page. Let's see, can we go to that? Is that my books have errors in them? That's one of the things that happens when you write books. You make mistakes, and so I'm very interested in people telling me about the errors so that I can get rid of them. And my publishers have now been very cooperative that they are reprinting the books sometimes more than once a year. Each printing corrects about 50 pages in some little way, fixing errors. Nobody has a complete set of my books, but they keep changing. But anyway, I pay $2.56 for each error that when it's first reported, and it's certainly worth more than that to me. But I want to mention that fact specifically tonight, that because I spend a lot of time trying to get those errors corrected. Yeah. Hi.
In my job as a proofreader, as a technical writer, recently I ran across a manual in which a manual for a database system in which contained the statement that it sorted files of any size in a speed that was linear with the size of the file. And although I was only the proofreader, I put a circle around this and said, can this really be possible? And sent it back to the head of the company. Yeah. And I got back the reply, anybody who has read and understood Knuth on sorting will realize that this is possible.
That it is possible, yes.
I didn't realize it was possible, and I wanted to ask you to comment on the upper limits of the efficiency of sorting.
Well, it depends on how you define terms as.
You have to move the mic. We'd like to move the mic a little higher. Is that what?
Yeah. Now I can't hear anything. What? No? Is that all right? Hello? Okay. So should we start over from the beginning? Good night. Good evening. All right. So sorting in linear time is easy to do if you happen to know that the key has a finite size or something like this. But if you're sorting on the basis of comparisons between keys, then you can prove by information theory that it's impossible, because there are n factorial possible outcomes of the thing, and each comparison only divides these into two classes. But if you're doing some other, if you're using any other property of special properties, then it's possible to get around that bound in quite a few different ways. In fact, you can do sorting with zero comparisons. I mean, so you don't need n log n comparisons, as some people think. You can do sorting just by stuffing things into arrays and extracting bits and things like that. I mean, a radix sort, for example, takes, if you have a 30-digit, if you have a number of say 64 bits, you could do 64 times, divide the numbers into two parts, and always say, the way we used to do on a card sorter. And so you put the ones on the top, and then you sort in the next bit, and you do the same thing. You do that 64 times. That's linear, and you've sorted the number. Okay, Don.
I've written lots of computer programs, but the last one I wrote was 35 years ago. If I were to read the source code of commercial software today, would I be surprised or notice anything different?
Okay. Now, this is your question is in the form of if A, then B, right? So I'm going to So the hypothesis is that you're going to read one of these source codes for me, and the answer is you'll be quite surprised, because it's going to be it'll probably just be a call on some library function, and you'll need to. They call it open source. That means you have to keep open 10 books of reference. Now, actually, I love many of the goals of open source, but I don't like this fact that every software system believes that they have to make the universe that over again, and also a lot of these things you could do in 2 or 3 lines without using libraries separately, but there's a big difference there. But I think you'll find that there are some ways of doing programming now that are still fun, and I encourage you to do it. You know, your first program now should be to say "Hello World," of course. And if you find that fun, then go on and write "Goodbye World." Yeah. Okay.
I was hoping I could get you to speculate a little bit. If hypothetically, suddenly there were no more computers, you know, if we just like electrical appliances were discovered to be drying up the ocean and sending the Earth out of its orbit, what would the direction of computer science research take? What would it look like?
Well, that would certainly make it easier to write my books, I must say. I don't know. I guess we'd all become like Don Parker and be thinking about the old days when we wrote programs. No. I think that somehow, for example, let's take another scenario that all of a sudden quantum computers work and they're so much better than others that nobody uses the present kind of computers anymore. I would still sit with my Linux box and have lots of fun. But now, if I couldn't use that at all, and if I just had to play mental games, I don't know if there's any other mental games I'd be good at. So I might still, try to imagine that I was programming a computer like this. I'm very limited in my capabilities, but fortunately they correlate well with the present kind of machine. Question back here?
So you've almost answered my question. You're working on volume 4 of The Art of Computer Programming. When would you expect there'd be enough material to start working on volume 1 of The Art of Quantum Computer Programming?
Okay, so so I think that's actually quite a different way of thinking, and it might be that people who are well versed in today's kind are able to adapt, but it might not be because quantum computing is it doesn't have a while loop in it, for example, and so it's very different and therefore I don't feel confident in answering that kind of question, but it seems that we might need to take our audience from a different population. I mean, the programmers might have to come from a different part of a segment of society, or it might not. But that's my take on it right now.
Yeah. So in computer hardware, it's been semiconductors anyway have been tracking Moore's law fairly closely because nobody dares blink and get off of it, and it's not clear that somebody has tracked the same sort of law or self-fulfilling prophecy or something for programming requirements or things that you can do with that. Do you see that there's a separate trend between the two that I mean, in the old days it was you could barely get your program into something, and now it seems to be there's tons of space. And is it on its own different trajectory?
I don't know that. That's a kind of a thing that goes beyond my expertise. But my personal take on it is that Moore's law has been going faster than we can think of things to do with it. But faster than we can actually finish the programs. We can think of lots of things to do with our computers now, but it's hard to go to sleep at night because we want to do some more because it isn't easy to use the capacity of the machines we have. But it's easy to think of more things we could do with the machines we have now for improving almost every aspect of life. It's just that we don't have enough hours in the day to finish our work. I've been taking too many from this side. And I know how it feels to be in the audience on the side where the speaker's always looking this way, So I'm going to try to stand over here for a minute.
So I have an easy one. You mentioned the interest in the people finding errors in the books, and I recall seeing tacked to some colleagues' board check from you for having found an error. At least I think I did recall seeing that. And if you did send all of those out as checks, question would be, were any of them ever cashed?
Were any of them ever canned? Well, now there's a guy, is Bill Love here? No? Anyway, there's a guy in San Mateo who cashes one every month. But you know, wherever you see this, just tell the guy to Xerox it and cash it, for goodness sake. He can always put, you know, some people lately haven't been cashing them. You know, some of the, well, over the years, I decided I'd kind of, so over the years I've written more than 2,000 checks, and the average is a little more than $8 per check. Now I only report on my income tax the ones that you know, for expenses of doing writing. I only report the ones that clear the bank, I used to report all the ones that I wrote, but I stopped doing that about 10 years ago. I don't know, before the IRS was going to check up on me. But people aren't cashing them quite as much now as they used to. Yeah.
Hello. Over here.
In 1900, David Hilbert listed 23 problems for the future of mathematics to solve, and I was wondering what you see as far as the fundamental problems that need to be solved for computer science for this new millennium.
Okay. Well, I'm no match for David Hilbert, but I did pose one such problem when I gave the keynote address at the IFIP Congress in San Francisco. That was maybe 10 years ago, because I thought it was probably the only time in my life I'd ever be the chance to give a keynote address, and Hilbert was sort of the keynote speaker when he gave it. So I said, okay, let me give a computer scientist a problem. And the problem, let's see, can I refer? Do I have a website where I could point to it? I don't think so. It's reported in this book. Where is it? It's called this one here. And this book has a chapter called Theory and Practice 4. And that's that keynote address that I gave in San Francisco. And at the end of that, the answer is, what goes on in a computer during 1 second of time? I was thinking of the analogy to the, you know, a biologist will go down to Central America and look at a rainforest or something, and they'll take an acre, that rainforest, and they'll survey all the plants in that acre and get some idea as to what really goes on in the world, in a part of the world. We don't know what goes on in our computers, and so I wanted to take somebody take some random second of what a computer is doing. They'd have to have access to source code, and study exactly what it is. And maybe, you know, people in different parts of the world would do it, and they would both find interesting segments. But that's a problem that I would like to pose to somebody in the audience. Nobody has responded to that one yet, and I'm waiting. I think that would shed a lot of light on how to make our computers better. I did a similar thing 30 years ago when I had a group of students at Stanford, and we went around taking Fortran programs out of the wastebasket at the comp center and finding out what kind of programs people were writing, actual programs used by, and we studied these programs. You know, we studied randomly chosen programs, and that we made an empirical study, and that became beginning of a valuable kind of software engineering research, and I believe a similar thing would pay off.
Your work in the area of algorithms is legendary, and I remember in college being able to develop optimal algorithms for garbage collection and for allocation of resources in an operating system, and I used that quite handily from time to time, and we were desperate on memory all of the time. Now we're in an environment where the processors are as big as mountains, and memory is as far as the eye can see. What is the value of doing small, tight, and elegant code in a universe where you have Java interpreters that frequently dump megabytes of garbage and wait 20 seconds or so before they ever even need to grab anything.
Yeah, well, it depends on, there are certainly times when it doesn't, when there's no point in having an optimum solution. When it's a one-off problem, then you're only, and it's a difference between a millisecond and a second or something like that, and you just want to know the answer to a problem. I was playing around last week with alphametics. These are the famous one is send plus more equals money, where you have some words that you're supposed to substitute digits for the letters, and it's supposed to make sense as a sum. And so there's only 10,000 ways to assign a digit to the letter. I mean, sorry, 10 factorial ways to assign digits to the letters, and that's 3.5 million. We can run through 3.5 million possibilities. You know, there's a way to do it so that you're only using a few instructions per one. So you can do it by brute force, not use any thought whatsoever. And on the other hand, if you have a whole bunch of these problems to solve, which I did, I started to make problems of the form, well, you know, 2 plus 3 plus 5 equals 10. Well, that wouldn't work, obviously. But the question was how many such sums that are true both semantically and alphabetically would there be? So now I was solving thousands and thousands of these problems, and so then it paid to have a better method. Now, as far as saving space is concerned, that seems to for the near future, good ways of economizing on memory are always going to be good, except for a problem that runs, you know, that just runs real fast and is out of there, because the memory speeds are not keeping up with Moore's law. The gap between references to main memory and processor speed is getting larger and larger all the time. So that I now measure the cost of an algorithm in terms of how many memory references it makes, instead of, you know, that's a number that's going to. It still depends on the locality, like how many cache misses you have and things like that. But I'm using memory references as a first crude approximation. So I call it MEMS, and I mean I'm talking about kilomems and megamems and things, you know, as a unit of time for comparing algorithms to each other. If you have a smaller number of things in memory, you're saving a lot of time, and if you can keep it compact, then it's all in the cache as well. You can download it faster when you're sending your applet to another computer, etc. I've got to go over to this side again. Hi, wow, I didn't know you were on the West Coast.
I'm here for tomorrow.
Oh, I see.
I don't have a microphone, but I can make this work. Early in my career, I happened to stumble across the Bloom filter. And about every 7 years, this algorithm reared up and became incredibly useful for a problem. You know, in routers or phone switches or whatever, it was just the right thing. Is there an algorithm that you know that you think is it's not used very much, that is especially handy, that you think people might be useful for them to chase down or to put in their toolkit?
Okay, well, that, you know, at this conference that you and I are going to go to, I'm going to talk about a few that I hope will come back. You know, but certainly, as I write Volume 4, I run into many algorithms that exist and are waiting for an application. I mean, really, there are. It's you know. Sometimes the hardest thing to do is take a general method and find its special cases. And that's the best way to understand it. You know, just think of various special cases where it works. So some algorithms that are based on matroid theory, for example, will solve incredible problems efficiently, but we have never run into those problems yet, as far as we know. Except well, this word matroid is kind of a scary word, but it's sort of a generalization of the idea of when vectors are linearly dependent on each other. But in trivial cases, you can say that a set is linearly dependent if it has more than 5 elements. But any set of less than 5 elements is okay. And for example, and so you can specialize any of these general matroid algorithms and say, well, what happens if you use it on a trivial matroid like this? Then you might get a problem that you say, oh yeah, that's one the guy asked me about last week. It's a very good question, but the way I do it is I try to find all the algorithms that are somehow short and easy to and easy to understand, and then I try to specialize them. Like you mentioned, Bloom's method of binary hash coding, or whatever you call it, where you superimpose coding that's used for information retrieval and various things. Somehow every simple method somehow finds its home, and you want to learn when you get a simple method, you want to learn the special cases of it and file those away. So that's all I can say.
A few years ago, the ACM was 50 years old, and they had this conference, the theme of which was, what is computing going to be like in 50 years? And I wondered if you had any speculations on that, and also on what programming would be like in 50 years.
Okay. Yeah. I declined to participate in that conference. And I mean, you might say it's a cop-out, and it probably is, but let me say that the reason is that somebody asked me once, they were interviewing, and they said, well, what was the most surprising thing about computing in past time? And immediately I had several answers to give. And then she asked a question I'd never been asked before. It was, what was the least surprising thing about computing? What would you have predicted? And I was stupefied. After a minute and a half, I said, "I'm sorry, you got me." Yeah. So as a prophet, I'm a loss. Yeah.
Would you say that computer science and computer programming is more art or more science?
Would I say that computer programming is more art or more science? Okay, so this is something where I've said over and over again. So you probably know what answer you want me to give. And I called my book "The Art of Computer Programming," using art in 2 senses. One is the idea of beauty, where you like to have a computer program that is actually cool, beautiful, and like a poem or a symphony or something like that, something that you can be proud of. And the second thing is that it's an art because it isn't yet a science. That is, it's something that we don't that is not well understood yet enough to be done automatically. And so when I studied what people meant when they said that something was an art or something was a science, I came to the conclusion what it means is that if we understand something well enough to program it, then it's a science. And if it still takes human beings to think about it, and I guess David Stork is going to talk about that future, then it's an art. And so, and what seems to happen is that every time that every year it becomes more of a science. We understand more and more, but the art continues to leap ahead and stay way ahead. And so once we learn more about it, then we still have more that we don't know how to do automatically. And that's the sense in which I think it's more of an art. And I don't see science ever catching up in my lifetime.
Hello. I've read recently about...
Okay, but we have to have you next. Okay. Yeah. Okay.
Sorry. I've read recently about some interesting algorithms that try and solve problems more from the bottom up in terms of kind of an evolutionary approach where they combine different snippets of algorithms and then have some weeding algorithm where they take the ones that were more successful and go from there. And they can do some simple things like propagate a program around the network or build something that climbs over a wall. Do you see any future in those kinds of approaches and methods for solving complex, sophisticated, intricate problems, or is that something that will always require human intervention?
Yeah, well, I don't see it as solving all problems of the world, but I do see it, but it's done some amazing things. Let me show you one of them, I think. Let's see, go back, go to Stanford Graph Base. Where is that? Stanford Graph Base. Here we go. So in this book, I have a collection of little programs that I was writing as aid to writing Volume 4. And one of the programs was the following. I put in, as a database, I put in all the football scores from college games of 1990, which was the year I was working on it, and also from the A teams, and also a couple AA teams from the Ivy League. And so for example, you could say that Stanford beat UCLA by 5 points, and UCLA beat Arizona by 20 points, and so on. And you keep going through a chain of games, and you find out that Stanford beat Harvard by 2,300 points. Now, the question was, what was it's an unsolved problem to find the best such sequence of games that would maximize the amount. And I put it as a challenge in the book to see if anybody could do better than the method that I had. And this guy, let's see if it still exists. He used a genetic algorithm. He said, my best solution was 2279, but Buell-Chandler has improved that to 2448 by applying genetic programming ideas to some of them. So, you know, there are certainly a variety of problems in which this mating type of algorithms are really good. But there are also problems that I don't see how it, at present I have no idea how I would ever get anywhere close with it. These problems that somehow, if you're near the solution, it doesn't look like you're anywhere close to it at all. So there are some kind of problems that for which this is incredibly powerful, and this jumping over walls, it blew my mind when I first saw it. And other problems where well, it doesn't get around the problem of P equals NP.
This is a question in the category of art. At one time in your life, you mentioned that you were a fan of Tom Mix.
I was a fan of Tom Mix?
Yes. I was wondering, when was the last time you saw a movie starring Tom Mix?
Yes, I've never seen them. They don't exist. I've asked David Packard to see if he can find any in any of the archives. They seem to have all disappeared. I had a computer named Mix, and that's how come I got interested in him. But I didn't know him, you know. But I found out that he was, you know, was a real cowboy. Then he became a Hollywood movie star. He wrote a column in Variety magazine every week. I went to Stanford Library to look these up. But I also found that almost none of the perhaps none of the movies he was in have survived. And so if you've ever seen one, let me know.
I'm interested in your opinion of the patenting of algorithms.
Yeah, I think it's a big mistake to patent algorithms. It's like mathematics. It's, you know, you don't have a patent on the number pi, and I think especially it's horrible when a trivial idea, a trivial algorithmic idea is patented. By trivial I mean something that I would expect any student to be able to come up with in a take-home exam.
And that's happened a lot?
And that's happened a lot. But fortunately, this Patent Institute came out where they tried to patent all the trivial algorithms they could think of, and you know, and then give the rights to anybody who wants before somebody else did it. But I personally think that that algorithm is a mathematical object, and mathematical objects are inherently not patentable. I wrote an open letter to the Commissioner of Patents. I don't know if he ever saw it, but Stallman talked me into writing this letter. And one of the points I made in there is what would happen if lawyers would take out like a patent on all the precedents. Every time they win a case, they win a case and somebody cites that case, they have to pay a license fee for them and so on. You see how that would make it harder for lawyers to go. And I think this is I couldn't have written tech if I had to worry about patented algorithms. So fortunately, I wrote tech in 1977, 1980.
The problem of self-reproducing programs has been studied a fair amount. However, using 7-bit ASCII, what is the smallest such program that you're aware of, and what programming language was it written in, and can you prove that it's the smallest one?
I believe that there's some kind of a theorem due to Gödel that you can't prove something about smallest possible programs that are self. I mean, maybe you could. It's similar to a busy beaver. Somehow the busy beaver problems where you try to write a program that will stop, but take the longest time to stop before it does. Seem to have to be looking at themselves in order to do this, and so it's a similar thing. And there you can just conjecture that you have a good one. But sometimes actual proof that I can't say this is actually impossible to prove it. But now language for self-reproducing programs. We used to. That was one of the hot topics in Datamation or some puzzle page, right? And I don't know if anybody's done it with Java now, but we used to, every new language we always used to see what was the shortest we could do, so people who are into logic would like this because it's a nice application of the recursion theorem to construct these programs. And my late colleague Bob Floyd was the best in the world at constructing them, as far as I know.
Some time ago, I was looking at the issue of the human brain and trying to figure out just exactly how much data capacity it actually had. And it's got 10 to the 11th power neurons, and each one of those can have 20,000 dendrites. And then I started realizing it's far more than a bit per dendrite because of all the permeable combinations of neurons that can be interconnected. And I was wondering, what your thoughts were on the total memory capacity of the human brain.
Yeah, it boggles my mind. The thing that really boggles my mind is the slow cycle time. I mean, the brain has to go through 7 levels of logic per phoneme that I'm saying to you. You have only 7 layers of logic in order to interpret the words that I'm saying to you this moment. Now, I suspect that the brain might be doing this by some kind of a genetic algorithm. It certainly has to be massively parallel, whatever it's doing, and so maybe it's having some kind of a breeding of hypotheses about what I'm going to say next or something is, and the fittest is surviving and getting into so on. That might be able to do it at such a low cycle rate, but I have no clinical experience in this, and I know that there are now better and better ways to measure the electrical pulses. We had a great lecture in our department a week ago by apparently you can put probes in the brain, and we don't have pain cells in there, so you can put electrodes in there, and they're trying to so more and more information about what the neurons are doing is getting through, but it seems that also these neurons are turning themselves on and off a lot. That they, there's famous experiments that sort of changed the main paradigms. A year or two ago, when they found out that when they tied some monkey's fingers together or something, then all of a sudden his brain started changing the way it responded to things. And my guess from being way outside the field is that probably this happens, that the brain rewires itself much more often than that, and that's the common thing, and it's not really a surprise at all. People are going to look back at this 100 years and say, oh, they thought it was a surprise. But I'm way outside in this. It's even farther than quantum computing from what I do.
Yes.
I would like to know your thoughts on software maintainability and why this problem hasn't been taken more seriously, and why when you learn programming, why they don't teach you to read programs before writing programs.
Now, the question is, what are my thoughts about software maintainability? Okay. My thoughts are all expressed in a book. Okay, so somehow Stanford is down. Wait, we don't have this. What can I? Okay, stop. Let me try it here. What? No, yeah, right. Google will have a cache page, right? No, I think the network has just gone down. I don't think we can get anything. No, wait, I did go back, but back was easy. Yeah, okay. Okay. So anyway, this is my own take on the subject. Doesn't seem to be right for everybody, but my answer is that the best way to maintain a program is to have the program well explained, and the best way to explain a program, I found, is to think of it as a hypertext, as a web composed of simple pieces that are hooked together in simple ways, but making a complex thing. Literate programming is a very simple set of software that makes it easy for you to use this discipline. And I don't. Well, there's a whole kind of references here to to introductory things, and do I have an example of a literate? No, that would take too long. But now on my news page, I said there's a major new release of CWeb about this, and it was because it's now very easy to use with Acrobat Reader. So when you write a program in this language that I use for all my programming, CWeb, it immediately comes out, and you can click on things and find out how to get around the program, and it's a lot of fun. And for me, it's the best thing since sliced bread, but that's because I invented the darn thing, so I'm not biased observer. But I can come to, I have many examples of such programs downloadable from my home page. If you go down here, downloadable programs, you could take a look at some of these, and I don't think we've installed the software on this machine, but we could. Like here's one that you can just for fun, you can read. This is the source in CWeb for Adventure, the original great cave exploration game, and I tried to and I took Don Wood's original Fortran program, converted it to CWeb, and tried to make it something that is sort of the best possible documentation of a program. So if you were the maintainer of Adventure, this would be the way to do it. And if you find an error in this, by the way, I pay $256 for this too. Yeah.
The Google search engine searches 2 billion pages in 2 seconds. And if you're not impressed with that, they'll link you to their competition to show just how good that is. Did you have a hand in that?
Only that I rode in a car with Serge a couple of times, and we discussed algorithms. I doubt if I had any. No, I think Jeff Ullman, if any of the professors, Jeff Ullman and Rajiv Matwani at Stanford were involved with very heavily with that, but not me. But I love certainly I take most of my questions to Google.
I'm going to go back to literate programming again. I was
had been experimenting with it since a short while ago. I was surprised how back it dated, and actually it didn't cut it for me exactly. But I was surprised that you made that effort way back then, and since then nothing much has changed in the way the programmers interact with in the way that they describe what the computer is supposed to do. Do you envision in, I don't know, maybe not, of course not the short future, but anything in that direction where we would be beyond the text-based data structure where we express ourselves?
Good question, but I have no good. Everyone keeps looking for a nice magic bullet that's going to make programming easier. But as far as I know, the problems are very subtle, and the best way I know to do it is to just have better ways for us to keep our brains going into it. But it's an art more than a science, as far as I know. It would be nice to just, but you can take certain classes of programs and solve them that way. But that's what that means, that you've made part of it a science. But then you'll think of many other programs that won't be doable that way, and you'll have to go back to the hard problem.
Completely independently of literate programming, the programs that you write seem to look different from programs that a lot of other people write in terms of what things go on the same line or different lines, how things are indented. And I was wondering if you could say something about how you format programs and what the philosophy is behind it.
Yeah, I just sort of grew up with a certain style that was used in ACM publications, and it seemed natural to me. So when I came to automatically formatting a program, I used that particular style that seemed more comfortable. These things could be changed. That's not the key idea of literate programming. That's a minor thing. It's a matter of taste there. The key idea is treating program as a piece of literature for a human being to read, and dividing it up into modules and making it easy to see how the modules connect to each other. But I thought you were going to say other things about my programming style. Like I use open. In C-Web, you can just say, well, let's take a look at an example of what we might say here. Well, let's see, we should have a bigger font. Preferences. Where are the preferences? What? Edit. Okay, yeah, edit preferences, thanks. Okay, fonts, and this is typewriter type, right? So, fixed width font, okay, let's go to, come on, 24. There we go, okay. So, this is an introduction. So now we get into, okay, so in C-Web you can say, initialize all tables. And then throughout your program you can have a part saying initialize all tables also includes the following table that I want to initialize. Instead of in a regular programming language you have to put something in the order the compiler wants to see it, but in literate programming you put it in the order that you like. Then it says simulate an adventure, going to quit when finished, deal with death and resurrection, print the score and say adieu. Now, those aren't subroutine calls. Those are macro calls. Those say, it says stick that code in here. Now that's a big difference between the way I write programs and the way a lot of people write programs. But I don't need subroutine calls. I have a good way to avoid the subroutine call overhead. I have to be a little bit disciplined in the way I could break all kind of rules about private and public variables and things like this, but I don't have to, as long as I'm writing the code, by myself, I don't have to worry about that. So that's probably the biggest difference in my programming style. And if I were working on another kind of environment, I would do it with subroutines as I did in the Stanford graph base. Yeah.
So I've got a historical question, and I'm curious where it goes. Right now we're seeing
language wars where you have like Java on one side and C# on the other, and companies are using the tools as I guess, weapons in the battleground. I don't know if that was true in the early days, if C was
Yes,
being...
yes. In fact, it's same old, same old. I mean, it's at least since I was 10 years old. Yes, it's the same, and also people are trying to find them. But fortunately, that keeps a lot of people's energy tied up while I'm writing The Art of Computer Programming.
What made you
Why did I
decide?
become a computer scientist? You know, I always went. It was because I mean, the real turning point was when I was a sophomore, and I looked at some programming manuals were put up by IBM in 1957, and the programs in there were really stupid. And I said, my gosh, those are professionals, and I'm only a sophomore, and I can do better than that. So I decided to go into programming. Now I didn't realize that almost anybody in the world could have done better than that, you know. But that's the truth. That's the truth. I just found out I was good at it, and it was fun. Yeah.
Going back to your programming style here, I believe you once claimed that your programs don't have bugs.
No. I have never. No.
Because you desk check them until there aren't any bugs.
No, this is that was Dyke's.
Okay, that was an urban myth, huh?
Yeah.
Well, okay, all right. I thought that was too
I
good
have
to be
never
true.
seen a program that I would be confident to say that about.
Well, let me ask a related question then. It seems to me, though, there is a lot of value in desk checking your code.
Yes.
But today's programming environments seem to be, with its highly interactive nature, leading programmers away from checking in favor of try it out, see if it runs, and then hack it into existence.
Well, you know, then you should hire somebody else. I mean, these people will learn it. I used to write programs that way, and then Bob Floyd taught me the other way about 1960. I didn't even realize that there was a way to use any something that I could really know that my program was right. It was a revelation that there even existed such a thing. Now we've got these things, but they only go so far, and so people say, well, let's not use them at all. That's dumb. I mean, you want to use your life preserver if you're on a boat. I mean, you still want to know how to swim, but.
Have a question about the sort of monolithic versus distributed nature of programming. It seems that somebody learning how to program maybe 10 years from now will be presented with a model of a network of machines, and sort of starting from there, you realize that right now there are millions of very, very fast processors basically sitting idle, and that our ability to produce fast processors doesn't compare with our ability to use them. There have been efforts to make distributed use of processing capacity, but it seems that it's been pretty primitive in the brute force crack codes or do signal processing. I guess what I'm wondering is what's keeping us from using the resource of a huge amount of connected processing power, and is it a programming model problem? Are there interesting algorithmic problems to solve?
So certainly the problems, the last question is the easiest. Certainly there are a lot of interesting problems to solve whenever you try to make something work with cooperating people from many different cultures and disciplines, and somebody wants to, but a few people have successfully made models of this where you can allow your computer to run problems. Part of this search for extraterrestrial intelligence, or find a new Mersenne prime, or there's a whole variety of problems that for which there are thousands of processors working on as we speak on these things, and they have no practical value at all, but the programmers are glad to have it. It's better than than just an ordinary screensaver. And then they have to worry about how to distribute this among all the people and collate the results and stuff like that, and not to handle legal issues about invading somebody's machine and so on. So that quite a few people are working on exploiting this unused power, but they're not going to use my machine because my machine at home is standalone. I just don't, I'm not on a network, and I'll run my own programs, but I just want to be sure that I never have a virus. I go to Stanford to use the net. Yeah. Well, I have another machine at home that I don't care about if it gets infected. Yeah. Yeah. Bruce?
I believe the urban myth was beware of bugs in the above code. I've only proved it correct, not actually tried it.
That's a frequently asked question.
Yes. Okay. Thank you.
What? No. Did you?
But we tracked it down recently, and you perhaps repeated.
I put that on my frequently asked question page. I hope so you can check and see if it agrees.
I'm interested in your opinion as a professor on the H-1B visas. Is 190,000 a year enough, or too many, or too few?
No, I'm sorry. I'm a writer. I'm not a policy expert. I think in order not to completely duck the question, I think in all my experience from the people that I meet coming into universities, it seems a very robust number that about 2 out of every 100 resonate with computers. They have this peculiar way of thinking like I do that seems to make them computer people. And that means that there's a certain number of people. Now, if this holds for everybody in the world, including the pygmy tribes, et cetera, we still don't have enough programmers. And so, how are you going to solve the problem if you have more people that don't have this way of thinking? They aren't going to write good programs. It's going to be a step backward. So there's going to be a shortage for a long time, no matter what the. I mean, this is why Silicon Valley can't have a depression. I mean, yeah.
Well, as a furtherance to what you were just saying, I teach an introductory programming class, and each semester I look out over the faces and I try to decide which one of these people is going to be a good programmer. And I wonder if you would comment on the mental, psychological, or even physical aspects of being a good programmer.
Yeah, IBM has been, started running ads in the 1950s for chess players, hoping that would correlate with ability, and it's been an open problem. Now, my best take on it. Let's see. I don't know if we still have that one. No. Okay. Well, in this book, in this book on papers on computer science, I have one of the chapters there. Select the paper. Yeah, one of the chapters is called Mathematics and Computer Science and its relation to mathematics. And in that paper, I tried to study as well as I could what this crazy thing is that makes a computer scientist. And the two aspects that I think are most characteristic, although this remains unproved, are especially as distinct from a pure mathematician. One is the ability to deal with non-uniform structures that where you have case 1, case 2, case 3, case 4. Like, a program has steps 1, 2, 3, 4, 5. And so you have this kind of ability like lawyers have of dealing with facts that are are diverse. And the second is the ability to jump levels from high level to low level of abstraction. So you can see something in the large instantaneously you've seen also in the small. You know that adding 1 to this variable is going to be part of something that gets you to a high level goal. And you know how to go between machine language and assembly language and compiler language and high level language and abstract algorithms and so on effortlessly. Now these are the kind of skills that seem to need to be most strongest in there's one that I've identified so far, but there are probably others. I haven't noticed any physical thing, although my wife, I'm going to the hackers conferences. My wife said to me, we went to a picnic a couple of years ago. She said, "How will you recognize a hacker in this big public park?" And I said, "Well, they tend to weigh more." But that's because we have such good meals at the hackers conference.
I wonder what your opinion is of the computer language Forth.
Computer language Forth was a very great way to pack a lot of logic in a small space, and it sort of has PostScript as its greatest descendant of the present time. But it was a kind of a revelation in the early '60s that you could instead of writing a software using the computer that you have, you make up your own little computer, and then you make up your own language for that computer, and then you write a little interpreter for that computer, and you can pack an awful lot of logic into it this way, and you can also debug your program faster and so on. And so Forth was especially powerful in those days for writing games when you had to get your computer to fit in a small space. Your whole logic for the game had to be in a small space. But this philosophy of having interpreted language and stack-based became very, very well nicely fleshed out in PostScript. Yeah.
I would like to know what would be your recommendation to teach new generations of engineers, not just programming, but to write good code, how to put the seed of quality and discipline, because it seems to me that I didn't have the opportunity, the privilege to write code in the 1960s, but I think the code back then was higher quality than the code that engineers produce today. So the problem is education. What would be your recommendation?
Well, you have to make it fun. If you want people to write, you want to give them some tools that make it fun, or some make it some kind of that they get some reward for writing a good program in some way, and fun is one of those rewards. By the way, I think that it shouldn't be only me offering money for bugs in programs. I think Microsoft should say anybody finds a bug, you get a check from Bill Gates every time you find a bug. This would be a way to improve a lot. Yeah. I have a limit of, in my classes at Stanford, I had a limit of 3 per time. So this is your number 3. So be sure it's.
What is your most interesting algorithm?
My most interesting. What do you mean?
What algorithm do you find most
that I wrote, or
no.
that?
Of all the algorithms.
This is the top 10 type of question I said I was just worried about. Okay, so I love so many of these methods, but somehow the one that I worked most in my own life on was Euclid's algorithm, which goes back to maybe 300-400 BC, and I found that the mathematics underlying Euclid's algorithm is fascinating, and I spent a lot of time on conjectures, and then I found out that proofs of the conjectures, and then it got further and further, and now this brilliant young woman in France has found a mathematical theory that goes way beyond my expertise in explaining this, and there's great functions, complex variable that seem to have endless interesting properties that are all based on studying Euclid's algorithm from 2,000 years ago. So that has to be my favorite. There's guy waiting.
I hope I'm not asking you to be a prophet, or at least not too much. What do you think will happen of the PNP problem?
What will I think about the P equals NP problem? So that's the, you want to know the answer. You know, someone proved P equals NP by induction on N once. You know, it's obviously true for N equals 1. And then, then you have to go on. Now, P equals NP is certainly the most challenging theoretical problem. It's all problems historically that seem to be the most difficult are the ones that prove that you can't do something. Like, you know, you can't express pi with a ruler and compass, or you can't solve a 5th degree equation, things like this. You can't, you know, well, that's not quite, but anyway, and so P equals NP says there's no way to solve a problem where you have to do a certain number of guesses without guessing somehow. Now, it might be that the worst case scenario is that somebody proves that P equals NP, but we don't know why. But it's just an existence proof. In other words, there exists a polynomial time way to solve any problem that needs these non-deterministic guesses. And the reason that this polynomial exists is because there are only finitely many obstructions to it not existing. And since there can only be finitely many reasons why it doesn't exist, it must exist for some polynomial of some degree. But we'll never know what the polynomial is or what degree it is or anything. We'll just know that it's there. So that meant that the whole question, P equal NP, was the wrong question to ask. Now, you know, that's a possible scenario. Another possible scenario is that Andy Yao will solve the problem because he's been working hard on it since he's been retired, and he was inspired by Andrew Wiles, who solved Fermat's last theorem. They're both at Princeton, and maybe Andy is going to tell us all next week that he's solved it. But it remains the most famous open. It belongs on a list like Hilbert's problems, and in fact, there's $1 million reward for it now by this institute. Yeah.
Don, what tools do you use to create books?
What tools do I use to create books? Well, I have Emacs. No, I have Emacs and tech, and then I have, you know, I use Emacs for my database. I have indexed all of my files, thousands of lines of entries, but I just search it with Emacs. In fact, I've got a hack on here called color mode for Emacs, which I use with my database, which says you can if you look under downloadable programs under color mode. You can wherever your cursor is, you can say make that line yellow or make that line blue or something. And so I have color code for all the entries in my files as to whether or not, you know, I think the thing is great to go ahead with it, or I think it's too complicated for me, or haven't read it yet, and so on. So I build up a whole bunch of Emacs tools that help me as a power user of that. You know, I haven't added pedals to my computer yet for extra, but I use all the function keys.
Is there any work going on with regards to program correctness?
Is there any work going on with respect to program correctness? Yes.
I guess I'm thinking in terms of the subject of physics. In physics, there's the experimental physicist, and then there's the theoretical physicist. And I've been experiencing, I've done a lot of programming, and there's always a big group that does testing that proves the correctness of your software. But I always wondered whether there's the theoretical side to it, or is there any work going on in that arena?
Yeah, it's a huge research area that, and at Stanford, it probably is John Mitchell would be our main person, but there are many people all over the world working on these things. They still aren't anywhere near being able to take my program for tech and prove it correct. All these things are, there are. I have to say one thing though. Some people seem to believe that you could actually prove something correct, and that would be the end of it. But you don't know that there's not a bug in the checker, or you don't know that there's not a bug in your specifications. That you said prove that this program meets these specifications, but you didn't. They weren't really the specifications that you wanted. If you wanted to rely on put your life on the line as to whether or not there's a bug in some program, you still wouldn't want to use anybody's supposedly proved correct program. Yeah.
How would you rewrite tech?
How would I rewrite tech? I wouldn't. I mean, I think that there's a point in which stability is better than bad feature. And when tech reached that point, I was very happy to move on to something else. While I was working on tech, I learned this lesson. See, I was in the Stanford AI lab, and we had 4 guys there who were really great software programmers, and they were improving the operating system all the time. And every day, the operating system got better and better, and every day, we had 5 hours of downtime. I mean, because it was crashing. And so I wrote most of the tech book during downtime, waiting for it to happen. The next year, the budget money went out, and these other guys had to go over to Livermore and work on another project. We had only one person staying. He wasn't changing the operating system. He was just fixing bugs in it, not improving it. And it was wonderful. And so I decided that that's what I wanted to do with tech. I wanted to have something that people would, it would be stable and reliable. And now, that's not to say that it should last forever, but for me, it was enough for me to go on to the next thing.
Don, let's take one more.
Oh,
Mike, yeah.
I guess I got lucky. In your characteristics of a good programmer, the one that I was waiting to hear, because every good programmer that I know, including you especially, is a good writer, and I didn't language skills.
Well,
what's your take on that?
Yeah, I'm not sure. I've known good programmers who were a little bit challenged in the language area, but they haven't. But literate program, that's the real problem with literate programming. I said that 2 people out of 100 are going to be really good programmers. But how many out of 100 are going to be really good writers? And maybe, so maybe literate programming needs both. I don't think necessarily. I mean, I tried it out on a small sample. I had 9 undergrads where we went through the experience, and 7 of them worked well on. 1 guy hated it, and the other was okay. And it's a very small sample. But certainly language skills are important for literate programming. You sit there with your thesaurus, I mean, in order to find the best word to describe, or the best name for a certain variable or something like that. Because you want to communicate, it's the same as literature. But I have known people like the guy I wrote a compiler with in the '60s who really was a terrible writer, but he was a very good programmer. It's not necessary, but I certainly I found in my own experience that as a student, writing was about half of what I needed to do in life. So I practiced hard on that when I was young, and I make my students at Stanford the same way. I would be teaching a math class, and I would take a week off to teach writing. Because they weren't getting it otherwise. I gave a talk once in Sweden. There was a big meeting of the KTH, the Royal Institute of Technology in Stockholm, and they were meeting with industry representatives about how to improve their curriculum, and they presented their plans for the next year. And we went to this nice island off in the bay, and they give presentations on how they were going to do it, and they were expecting me as this mathematician to say, oh yeah, we need a little more theory, in these courses. And so I said, well, where did the students learn how to write? And And that, it wasn't in their curriculum at all. And all the guys from Ericsson and the other industry representatives, yes, 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 let's have that. So writing is very important in whatever job you are, I think.
Don, I think we're going to close the formal part of it.
Oh, okay.
But we know you're going to be here. We're going to have
Yeah,
a
I know.
reception out back. We have to be out of here by 9 o'clock. But certainly, we can do something else forever. And here's a small token of our appreciation.
Wow.
From everyone for you. So let's give Don Knuth a great round of applause. Thank you, Don, for all of your contributions.
Oh, I got a picture of myself.
Could be on your cover of your book. Thank you, Don. Thank you. I hope everyone
nice to
enjoyed
see you here.
themselves. There's information in the back. There's
Oh, boy, an artifact.
the reception will be open until 9 o'clock, so please enjoy yourself. And I know Don will be around for some more questions up front. Thank you very much.